that you are a model to us all. Thank you very much for coming and sharing this with us today.
Thank you. So, as Sam said, I live in Maryland, Rockville right now, where I started the circle. We called it Art of Inquiry, and the logo was made by my great-grandfather-in-law. Can you imagine? So, how do
Let's
I
run the slideshow. I think if we go to...
I think if I go this way, it will work.
Here we go.
Thank you. So, why and how? Why? Because I was absolutely desperate. I needed something for my kids, and I wasn't able to find anything. And I happened to read the wonderful book by Alexander Zvonkin, Math for the Little Ones, and I think it will be soon published by MSRI. I highly recommend it both to math circle leaders and to the parents. So, and what do I do? How do I do it? We have weekly 1-hour sessions. We do a warm-up and a few harder problems. We have one teacher, me, with a high schooler who is helping, and they're great. During the class, we take notes on student frustrations and approaches and mistakes, and it helps me to make a better curriculum next time. So I print out the problems, so they have them in front of them if they want to. We also put them on the board. And kids are provided with various manipulatives, such as checkers, blocks, clay, toothpicks, mirrors, etc. Not fancy ones, but the ones that can help them out to visualize the problem. So I have group 1 for 6 and 7-year-olds and group 2 for 8, 9-year-olds. I have 6 to 8 students per group. Here you see our Halloween class. We have Ben, Art, Marie, Anne, and Vicky here, and a couple of more students are not on the picture. See, they are very engaged. They have their clipboards with the problems, and some of them are thinking by themselves. Some of them are discussing the problems as a team. So, obviously, compared to older students, they are jumpy, noisy, and have no good manners. They also have very limited math skills. Like this group, well, they feel pretty comfortable in the range between 0 and 20. So, and my older group is learning multiplication table. But they're very curious and enthusiastic, and they have very few mental blocks, which helps. So I would say start early. In early childhood, all the problems we encounter are new problems for us. So we have this intrinsic ability to work with the new problems, but by upper middle high school, kids partially lose this ability. They're taught to do it this specific or that specific way. So how do we sustain that? I think kids need to play with the problem without the pressure to get a specific result by specific time. They need to make mistakes and enjoy them. They need to learn to distinguish what is relevant, what is not. They need to learn how to ask complex questions and how to solve multi-step problems and how to adapt to new situations that arise as they're solving the problem, how to work as a team and respect each other's opinions, and how to reflect on a solution. This is all can be taught to very young kids. We don't need to wait for the high school to do it. So, what problems do the kids love? It's amazing to observe that they love to solve the problems they don't actually know how to solve, also known as insight problems. So they love to spend their time exploring the problem and then to share their work and results with friends and parents. This type of problems also motivate kids to look for insightful ways of solving regular problems that they encounter, approaching them from different angles and trying to recognize and avoid cliches. And while I don't know how to systematically teach students to solve those insight problems, I haven't seen any works on that. But my observations show that if the kids know that there is a beautiful solution to the problem, there is something interesting, it's not just a regular problem, they're much more likely to look for that solution and to find it. So what do we do? Group 1, warm up. Continue the pattern. So, a lot of discussion here. They were trying to persuade each other that their solution is the right one. They came up with many different solutions, but then they would ask each other questions and they would see that it doesn't work. So, the situation resolved when one of them put a pencil in the center, at the center of the figure. And they saw this reflection feature, the symmetry. The little ones do have problems with the symmetry. 6, 7-year-olds still don't feel what the symmetry is. They're having problems with mirror symmetry and so on. The older ones, it's much easier for them. So there is a way to, introduce more symmetry problems to young kids, and they do enjoy it. Problem 1. It is known that 2 kittens weight less than their cat mom. Do 3 kittens weight more? So, we had a lot of discussions here. Some kids were saying, yes, they are more. No, yes, they are less. And they were very happy about their answers, very confident. And then Ben came up with his very original idea. He said they are equal. See? So I asked him whether the kittens are well fed or not. And both he and Anne said that the kittens are very well fed. Well, there Art and Marie said no, they're little newborn kittens and they're very small and not that well fed. So, and this was this point where they actually saw that they cannot solve the problem the way it is given. And that was my point. Because I wanted them to recognize that this problem is undefined. And I think it's very important to give this type of problems to the little kids. Not only the problems that have a solution, but also the problems that are not defined, and you need to actually figure out what is wrong with this problem. Because I think in the real life, not in school life, but in the real life, you are much more likely to encounter an undefined problem, and you need to define it. Okay? So they liked it, and we continued asking each other questions that are not well defined as an activity. And we had a lot of laughing, and we really enjoyed ourselves. So matchsticks. Move 2 matchsticks to get 5 equal squares. Kids found this one to be a very easy one. It was amazing to see these 6-year-olds to find the solution like maybe in 3 minutes. So and they said, this was an easy one, and can we get more like this? So, and I expected this problem to be appealing to the kids because it's clearly defined, it's visual, it's hands-on, you don't need arithmetic skills to do it. So, bonus fun. Make a knot on the rope while holding both ends of the rope. It was a big hit. So it was very noisy. They were jumping around. They wanted to get this rope to try. They wouldn't leave the class when their parents came. So I had to leave it as a homework. Okay, so at least they enjoyed it. Now, this is about my youngest one. Now, getting to the harder material, group 2, 8 and 9-year-olds. Please take a look on this column. The question is, what does 2581 correspond to? Well, the younger you are, the easier it is for you to solve. One PhD in mathematics spent, I think, an hour solving this. Another one used Excel to solve it, and he did. Excel helps. So the kids were able to solve it really easy. Well, I'm not going to tell you the answer. If you want an answer, come to me after the class. It is true. Okay. Now, problem 1. How to fry 3 pancakes in less than 8 minutes if you can only fry 2 pancakes at a time, and each side takes 2 minutes? Well, in the course of our studies, kids grew very suspicious of constraints. So they tried breaking the cage. They would say, turn the heat on, or make thinner pancakes, get a bigger pan, and so on. Well, I do encourage this. I know a lot of people see it as a nuisance, but I do think these are all workable solutions. We can all use them in the real life. Well, why not? They're good. So, but now I had to introduce a tighter constraint. So then the way they were solving this, they used their palms to kind of visualize what the pancakes are, how do you flip them, and so on. But one ingenious girl, she tore 3 pieces of paper out of the notebook and experimented with those. And she was the one who was able to figure out the answer. So this one. Tony has 3 bricks and a ruler. Now, how do we measure the diagonal from A to B? This problem generated a lot of interest. So they started with, please give us a saw. So, no, let's give us a drill. And then they said, well, if you don't give us a drill, let's make it out of the modeling clay and cut it. So the last exclamation made them to think of clay and snow. That's why I do not discourage this side thinking. So to say, because sometimes you can come to very interesting ideas this way. So they thought about clay. They started thinking about clay, about snow, about the impressions you can make in snow and clay, and how to measure this diagonal. And then from there, even though I told them that clay is not available, they were able to solve the problems with the help of 2 other bricks. Now that they saw that they don't really need the brick itself. Okay? One day, an applied mathematician happily solved this by using a Pythagorean theorem. Okay, next one. Is it possible to put 5 checkers in such a way that each checker touches 2 others? This was a teaser. It is an easy problem. And of course, I gave them checkers. So they did the first one sufficiently quickly, I think maybe in 3, 4, 5 minutes. And they started the second part of the problem in high spirits. But they soon recognized that they cannot do it in 2D. Well, they're used to that. They went 3D. And there they entered an elevated state of almost there. So they would check each other's solutions and point out the errors. And it took us forever. The parents came in. They took the parents joined in solving this problem. So this is an exploration problem kids really enjoy to do. Okay. So As a summary, I would like to say it's never early to introduce the joy of thinking. That doing this is both enjoyable, educational, and inspiring to kids and teachers. I think that our society needs out-of-box thinkers more than ever. And kids need to learn to search for and to recognize the feeling of those insight moments. They need to get used to that, and they also need to distinguish between knowledge and understanding. And it's not the end, so I have a problem for you. Kids really enjoyed it, and they asked me to show it to you. So, the royal prisoner. Many years ago, a French king was taken as a prisoner by Spain. The Spanish king ordered to make the entrance to the throne hall so low that everyone would have to bow to get through. However, the royal prisoner wanted both to avoid humiliation and to show his despise of the Spanish king. What did he do? Huh?
Walked on all fours?
They suggested this as one of the solutions. As a hint, it is loosely related to the warm-up I gave to the first group. Yeah. Yes, that's it. Okay. So, thank you so much, and I really enjoy being here. And okay. Oh, don't.
Need an introduction to the Bay Area, maybe to the rest of the country. Tom Davis has been doing math circles for website,
Just, no,
Tom's
not me.
website, what is it, Geometer?
Geometer.org. I'll write it down.
Geometer.org was and still is a wonderful resource. You should check that out.
Yeah, the first thing I'm going to do is write down the address of my website because there's sort of complete write-up for the topic I'm doing today, and in fact, complete write-ups for a lot of other math circles that I've led over the years. And so the site is simply www.geometer, geomeper.org, /math circles, all one word. And there's an index there to all of the rest of the stuff. Well, I'm officially a mathematician. I was trained as a mathematician, but as soon as I went to work, it was an engineer. So I sort of consider myself to be a mathematician gone bad. And a lot of the math circle that I lead have an applied side. Like I did all my, almost all the work I did in the real world was in computer graphics, and those provide great topics for circles. You can do things in 2D translation and so forth. But the one I selected to talk about today, I called Geometry and Geography. And the idea is that, well, I think I'm motivated to do it because I realized that as a mathematician, when I was learning to do math, I was always very, very good at the calculations and so forth, but I didn't have a really good geometric intuition. And I found that over the years, if I sort of practiced on this, it actually got better. And so I assume everybody else has exactly the same problem. And so the topic here is related to visualization. If you have a problem and you have some actual things you can twist around in your mind and so forth, it gives you good exercises to get better at that sort of thing. I'm also interested in geography and so forth. The other thing that I like a lot about this topic is it can be used at almost any level. I've used it with third graders and I've used it with high school kids, asking almost the same questions, but I sort of expect we go for more interesting, more sophisticated answers when they're high school students, and the third graders are fine. I mean, the third graders, the Earth is a perfect sphere, there's no problem. You know, and in high school you can say, well, it's not quite. You know, how does that affect the answer? There are a lot of things you can change. So there are all kinds of things here that it's actually sort of surprising. I mean, most people know that the Earth is a sphere because they've seen illustrations of this and so forth. But it's amazing even how many of them really have no idea that if it's day on one side of the Earth, it's night on the other. So they sort of have a flat Earth mentality, you know, until you actually pull one out and you say, okay, well, if this is the Earth and you know, here's the sun, you know, you can sort of see that I'm only going to light up one side of the Earth. So that's nice. You can and you can start out really simply. A lot of people know what the North and South poles are, but you know, what do they really represent in terms of what's going on? And again, a surprising number of people have no idea that that's the axis of rotation. But with a globe, you can get this. Most people know the Earth turns, things like that. So that's nice. You can certainly talk about North and South, day and night, things like that. But then another question, of course, is on every globe you ever see in the world, the axis doesn't go straight up and down. And so, well, why is that? What does straight up and down, well, in this thing, what does straight up and down represent? And it turns out that's sort of the plane of the solar system or something like that. So one of my favorite visualization questions to ask after I've sort of gone through the introductory part is, suppose that you're standing on the North Pole and maybe your feet are frozen to the ground so you can't move. You're always looking in the same direction. What does sunrise look like? So I don't know how many people here have thought about it. and a lot of people, a lot of the kids, you know, well, that's you know, you have the 24-hour day and night. And the guess is, of course, well, sunrise looks just like it does here. The sun comes up on the horizon and sort of goes across. But if you think about it, what it'll look like is the sun will just peak on the horizon and then sort of skid around the horizon. And by the time it's gone around once, it'll be up a tiny, tiny amount. And the next day, it'll be a little bit higher and so forth. And it'll gradually spin itself up to about 23.5 degrees and then spin itself down and disappear for 6 months. So that actually requires a lot of thinking, and you can do it by, you know, imagining a little person standing on the globe and where the sun is, and what does it mean that the year is going by. With little kids, you can have one kid being the sun and one kid, you know, carrying the Earth around the sun as it's spinning and so forth. With high school kids, you probably don't want to try that. But again, it's a nice topic. And so that's actually pretty simple. And then you say, well, okay, what does sunrise look like if you're not quite at the North Pole? Suppose you're off a little bit. You know, maybe halfway between here and the Arctic Circle. And by the way, what does the Arctic Circle mean? You know, things like that. And so then maybe they'll get the idea that the sun just barely peaks up at one point and then disappears. And the next day it peaks at that same point, goes a little higher, a little higher, a little higher. Finally, it's spinning around, but not exactly touching the horizon and so forth. So what else do I have on here? Yeah. What causes the lengths of days to change? You know, why do the days get shorter and longer, at least for us? And is there any place on Earth where the days don't change? All of this can be analyzed geometrically. You can, since this is a great circles, that's the topic of this, of our whole session here. There are some great circles here that you can talk about, and the equator's a nice one to think about. That, in fact, on the equator, the days don't change at all. The sun will come up and set at, in local time, it'll be precisely 6 a.m. and 6 p.m., assuming no mountains or anything like that. I remember a whole bunch of years ago, I was taking Spanish language classes in Costa Rica, which is about 6 degrees north of the equator. And I was living with a family and then taking classes during the day. And I would argue and argue and argue with the people in my family that the days do change length. There was just, they couldn't believe it. Because there, the length of days changed so little. But up here in North America, people are pretty aware that, that you do have longer and shorter days. What else we got here? Tropics of Cancer and Capricorn. Oh, that's a good question. Does the sun ever straight up? And of course, that depends on where in the world you live. But you can figure out, again, from the globe and where the sun is, exactly those points on the Earth where the sun might be directly overhead, where you'd get zero shadow. What else have we got here? Can the sun ever be directly north here in Northern California? Can it ever be directly south? Again, questions you can ask by looking at things on the globe here. What else have I got here? And there's no reason to stick with just the Earth. I mean, a lot of kids are interested in eclipses and stuff, and that's pretty easy to set up too. You know, you have another model for the moon and for the sun. You can do some nice geometry if you want. You can say, well, if you look in the sky, the moon and the sun are roughly the same size, but and you can actually write down the numbers. The sun is so many, million miles or so many miles in diameter, but the moon is a tiny little thing. What does that mean about the relative distances? Because they do appear approximately the same. What causes an eclipse? And then there are a couple of kinds of eclipses when the moon gets blocked and the sun gets blocked. How come there are lots more lunar eclipses than solar eclipses? They seem to come up all the time. Solar eclipses are pretty rare. Again, that's just a geometry thing that you can investigate with some similar, basically by, when you get a lunar eclipse, everybody on Earth can see it. When you get a solar eclipse, there's the one dot where the shadow of the moon happens to be sweeping across. Then you can ask about partial eclipses, what causes that, and you can see that by looking, since the sun is larger than the Earth, the rays are going to come down, and the shadow is actually going to be a cone that comes to a point. But you have this, what's it called, the penumbra, which is the larger darkened area. That's, again, easy to draw pictures of and so forth and visualize. Then there's the question of how come the moon has phases? How come? And again, that's pretty easy to do. You say, here's the Earth. If the sun's here and the moon's here, this half of the moon is lit, and so here on Earth we'll see half of it. And then you ask the question, if we had really good eyes and we could see the planets, do they have phases? And of course the answer is the ones that are closer to the sun than we do have phases, and the ones that are farther from the sun than we do don't have phases. And again, that's just a geometric point of view kind of thing, but it involves a little bit of visualization. Then you can ask, well, okay, let's look at the phases, let's say, of the planet Venus. And suppose you had a telescope. How are we doing on time? A telescope with a fixed magnification, and we just took pictures of Venus every 2 months and we put them together. What would the pictures look like? And it turns out when you have a full Venus, it'll be maybe a little tiny thing. And then you start to get the partial Venuses that are larger and larger, and then finally the crescent Venus might look like that. How come the crescent Venus is going to be so much larger than the full Venus? And that's because when does the crescent occur? It'll be when Venus is pretty close to between us and the sun, so the sun's lighting up mostly the back of it. You get the full Venus only when the Venus is on the far side of the sun, much, much farther away. I've probably exaggerated these a little bit. That's the idea. Then there are all of my favorite questions about the calendars. Why are things so screwed up? I mean, why is it 365 and a quarter days? And why isn't that exactly right? Why wasn't it exact? Why didn't we pick something? And the obvious answer is that there's no necessary relationship between the speed that the Earth turns and the speed that we move around the sun. Oh, and I guess I forgot another interesting question. Some of the Earth is tilted by about 23 degrees, and so we certainly get seasons. And you could ask, what would the situation be like if you were living on the planet Uranus, where the tilt is 84 degrees? You'd have fairly drastic seasons there, but it's, again, an interesting topic. What else do we got? Oh, so with the calendar stuff, you've got all the questions about using leap years to fix things up, and then the leap years you leave out because it's really not 365 and a quarter, it's 365.26, but then some of the leap years that you left out you have to put in again to make up for this error and so forth. That's a more sophisticated question that you might not use with the second or third graders, but it works out fine with the high school kids. Leap years. There's, what's a leap second? I mean, every now and then you read in the paper that, tonight they're going to add 1 second to the year because the Earth is actually slowing down, or whatever it is, we're gradually drifting out. Let's see. Why does a compass work? And why does it not work perfectly? That's again because the magnetic axis isn't lined up with the actual rotational axis. And you can sort of see, well, where on Earth would you have the worst results with a compass? I mean, can you ever have your compass with the needle pointing north, pointing due south? And then you can ask the question, the standard questions about, walking north a mile, south a mile, north a mile, east a mile, south a mile, and coming back to where you started and there's a bear, what color is the bear? And then you can see, are there any other places on Earth where that would happen? At the North Pole, it obviously happens. The trouble is there are no polar bears down south, so you would be pretty sure you were up north. But around the South Pole, are there any places where this kind of thing could happen? And it turns out there are an infinite number of them. But again, it requires a little visualization. Okay, that's I guess I'll end on the one I always toss out at the end. Quite often I've seen these same kids in circle after circle, and one of the things I like to emphasize is that usually in mathematics things are sort of logical and you can figure out things from the names. So if I say, well, how many sides does an octahedron have, and the kids have no idea, I say, what does oct mean? And they can usually think of things that have the OCT prefix on them. And, it's 8, it must be an 8-sided thing. And so then I say, well, we've got the months September, October, November, December, 7, 8, 9, 10, corresponding to months 9, 10, 11, and 12. And so the mathematicians obviously weren't in charge of that. So that's basically it. So, and as I say, on this site, you can get a whole long list of the questions that I usually use, and you can obviously add your own, and so on. Yeah?
I have repeatedly tried to figure out if the Earth, say, if the sun was over there and the Earth's coming this way around the sun, is the moon coming, if you're looking from above,
Is it the moon going the same direction around the Earth? Yeah.
I don't know if there's a logical way or if you need more data than I have, but I keep trying to figure it out from what I know.
The answer is I think that they're going this. In other words, if you were looking straight down at the sun and you saw the Earth turning one way, is the moon going around the Earth the same direction or in the counter direction? I think it's the same direction. Does anybody know? I think.
Sure.
Yeah.
But your data is just look at the phase of the moon, see where it goes through the sky, and watch it for a few weeks, and it's obvious which way it's going.
Oh, you say obvious.
Yeah. A lot of that stuff's not obvious to me either. Yes.
I don't know if this is true, but if it is, it's an interesting. The length of days graphed that is sinusoidal variation. You understand?
The length of days graphed over years.
If you graph the length of day,
You mean?
Hours of daylight?
yeah,
You mean over 1 year?
yeah, or over several.
Oh, I see. If you repeated it forever and if the Earth didn't slow down or anything like that.
I've thought of doing that as a project.
I can use the material on that project. I've done it in my trig classes.
Oh, great, yeah.
Well, it can't be true exactly because if you're sort of halfway between the pole, it depends on where on Earth, maybe at the equator or something like that. Yeah, Mark? Uh-huh. Oh, uh-huh. Further from the Earth. Yeah, that's great. Yeah, that's a good one. Yeah, that's the first answer when you say, why is winter? What happens during the winter? And it's, the sun's farther away, obviously. And that's the universal answer almost. The universal first guess.
Well, for a purpose about it being obvious, it's the sun rises in the east and goes in the west. It's a westward direction. The moon is going in the eastern direction compared to the stars. So you can then ask the question, do they have the same sense of rotation or opposite? And then you can look at the globe. But that's what's confusing.
For a lot of these astronomical questions, model, or at least a good.
I haven't looked. I wouldn't be surprised at all if something like that existed. On the other hand, this has never crashed. Okay. Yeah. As I say, you can have the kids moving around. I'm the sun. Here's somebody else is moving the Earth and spinning it around as to be the day and stuff like that. Yes.
Open-ended problems. Design your own universe with your own angles.
Oh, that's a good idea too. Yeah, invent your own universe with.
Well, the idea would be to formalize the relationships
Mm-hmm.
from examples to more examples in general.
Right. And I didn't mention. I mean, you certainly want to give them the relative sizes of the planets. Have this data available if you need it. How much bigger the sun is than the Earth, and how fast things are turning. Yeah. It's sort of infinite possibilities. But and you could obviously have incredibly difficult problems for advanced students. Like you could say, if you just make a sundial by putting a stick, what's the pattern? Oh yeah. I mean, I don't think I'd like to try that, but some of my students could do it, I'm sure.
Why not? There's something called the Leonard sphere, which is like a sphere, plastic sphere on with a grease pencil.
Oh, How big is it?
Pardon me?
How big is it?
I think it may be like,
A basketball, something like that?
and the other thing is a wonderful children's librarian who measured the Earth about Eratosthenes and the counts.
Oh, right.
Which is a very cool thing too.
Yeah, that's good. Yeah.
I've
Well,
known someone who's done that as an internet project who had people, kids in two different math circles or
the angles and
of the sun and tried to duplicate Eratosthenes.
yeah, great.
measurement of the Earth, size of the Earth.
Okay. Well, thank you very much.
Next, you got McFerron, who is a computer programmer by graduate school in computer science. She loves math, and she's very much on the sort of mathy end of computer science. And she has a
Computer had python.com on it.
last year results and
Oops. I'm stealing this.
she was at our math institute last summer, and she did this presentation with kids, and it was really, really fabulous. So I'm going to introduce Alex.
Just have to get my presentation on here. Okay. And I'm going to need this. Okay, so first of all, I'd like to thank Amanda and the Kaplans for being just such great mentors on math circles. I really love this, and thank you. Okay, so I talked to my mom. I told her I was going to do a talk, and she said, tell them what you're going to tell them, and then tell them what you told them. And I was like, okay, that sounds pretty easy. So here's what and then when I got here to San Francisco, my brother lives here. He picked me up at the airport, and I told him I was going to do a talk. And he goes, tell him what and I was like, wow, you guys have been talking about talking, and I need to know this stuff. So, okay, so here's what I'm going to tell you. I'm going to tell you Ramsey theorem, which is up here. I'm going to tell you a simplified version of it, which is the party problem. And then I'm going to give you the structure on how to turn this into a math circle. And okay, so let me start out with my personal history with this problem. I'm a computer science master's person, and I started the master's program a couple years ago. Of course, my math background was lacking, so I was kind of stressed out about this class I had to take called Theory of Computation. And I got the book. I'm going to start in fall. This is the class I'm worried about. I get the book ahead of time. I take out the book. I'm like, okay, I've got to read this many chapters. I've got all summer to prepare for this class. I cut it up into so many pages per day. I make an Excel spreadsheet. Okay, if I do like 10 pages a day of this book, I'm going to be totally prepared. I'm going to knock this class out. It's going to be great. I'm going to get a math tutor too, because it's been a long time. I've been working in industry for a long time as a programmer. It's been a long time since I've done some math. So I start out with chapter 0, which is the math background for this book. I get through everything until I get to this problem here. And I must have missed the little star thing that said, like, really hard problem, don't worry about it. And instead I was like, all summer I was freaking out. I was like, I've got to figure out this problem or I'm not going to be able to, you know what, I shouldn't even do a master's degree. I'm too stupid for this. My math is I can't solve this problem. I'm lost. My math tutor, I took it to her. She's getting her PhD in math, and she was like, I don't know. And then she had a friend who was an even more accomplished math person. We went to him, and the three of us were trying to figure this problem out. We were having trouble. So this problem plagued me all summer. And I even went on a camping trip with my family, and I was in the middle of this heat with bugs, and I couldn't stop thinking about this problem. I'm working out. One thing that's kind of interesting about this problem is, if you think about it, what it's really just saying, it's this easy problem to understand. If you have a graph, then what it's saying is you're going to if you have a graph of size n, you're going to have either a click or an anti-click of size. And a click is, so say you have this, a click is all the nodes are connected. So if this was your graph, this is the click. They're all connected. An anti-click is when you have, say they're not connected, but then maybe you have some other things that are connected over here. So these three are not connected. This is an anti-click, and this is a click. And the problem says, this problem up here, it says that if you have a graph of size n, you're going to have a click or an anti-click present in this graph to the number of 1/2 log n. Okay. Well, if you start analyzing this problem, the first thing you're going to do is you're going to start plugging in, values for n. And it doesn't really get big until you have about log 128 or something. And then that equals 7. So you're talking about a graph, just to get you're trying to solve this problem. You're talking about a graph with 128 nodes. I mean, how do you even, address that? Of course, me being a computer programmer, I started trying to write programs to analyze this. And this took me all summer, and of course, I never went to chapter 1 of the book, which was a big mistake that I'll talk about later. But all summer, even camping, plaguing me. the first office hours for the professor for the class, I go in a complete panic. I don't know if I have the math background, I'm lost in this problem. And you could tell the professor was like, gosh, the class hasn't started yet, you know. And he just tried to calm me down. He was like, look, find that quiet place in your heart. And I'm like, what is this guy talking about? He's like, breathe, you know, relax. Just find the quiet. And I'm like, God, is this like, I'm in a Buddhist temple? What am I? I'm at school. Help me with this problem. And then this other professor is walking by, and this guy tries to get rid of me and give me to another professor. The guy walking by, he's like, hey, Marcus, she's talking about Ramsey theorem. Can you, what, yeah. And then Marcus, who likes the stuff, took me into his office. And he's a German guy. I never met him before. He goes like this. He goes, oh, yes, Ramsey theorem. That's very, very interesting, very interesting. Okay, so what you do, it's very simple. You have six people at a party. 1, 2, 3, 4, 5, 6. 3 either know each other or 3 don't know each other. Think of this. It's a claw. This is a claw. Okay, hey, it was great meeting you. See you later. I was like, okay, claw. What is he talking about? I go home. I'm like thinking of claw. I keep drawing it out. Claw. How does this relate to that problem I had before? I have no idea how this relates. So I keep thinking about it, and finally I had one of those aha moments that was just, you know, the things that keep you coming back for more. I started looking at the people problem, and what I found was, so if you have 6 people at a party, and you know, and after thinking about it a while, I saw how it was related to this bigger problem. Basically, we're going to say the people. So the problem is you have 6 people at a party. 3 people either know each other, or 3 people don't know each other. I know that's kind of hard to put your head around, but basically what it is just a click or an anti-click. So what Marcus, the professor, was getting at with the claw is if you think of, if you think of one of these nodes, if you have a fully connected graph, everybody's going to be connected to everybody, or everybody's not going to be connected to everybody. The best way to do the proof is to use 2 different colors. Maybe some of you have seen this before. You use 2 different colors of pen or chalk, and you represent white, says, you know, they know each other. So. And then the other color is they don't know. Break it in half. Okay, so what Marcus was getting at with the claw was that you can kind of see that if you're going to connect everybody in one of the 2 colors, you're going to end up with a claw. You're going to have 3 of either red or white. There's no way around it, because that if you're going to connect everybody to everybody, there's going to be 5 coming out, but they're going to be different colors. So now the problem is simpler. Now it kind of gets down to, and if you think about it, it just gets down to this fact that you've got this type of structure. You need to connect the rest of these without making a triangle of the same color. Because if you have a triangle of 3 whites, and this represents knowing each other, then you've got 3 people who know each other. If you have, you know, so say you don't want to have a white, so you know you have to do this here, because this would create a white triangle, so you have to have a red here. If you went this way, you've got to have a red there. Well, then now you're stuck. You've got to connect these 2, and you have to use, if you use red, you've created a triangle here, and if you use white, you've created a triangle there. So that's the proof, and this was definitely an aha moment for me. I didn't figure it out with the chalk. I figured it out on the computer, but it still was a great moment, and it relates back to the bigger problem. So, how do I get? Okay. Are there any questions about this people problem? If there are, you guys, if you didn't follow, you could just come talk to me afterwards and we could go over it. Okay, so what I've just told you is the bigger problem, the Ramsey theorem, which is harder, and then I've given you a more simplified version of the problem. I'm not going to go over the proof for the harder one, but I did put it online. If you go to the list of presentations and you click on my name, you'll see kind of everything listed out, and I've also put the answer to the bigger problem, which is an algorithmic answer, and it's really cool. But I suggest trying it out on your own first if you haven't. Okay, so I've given you the Ramsey problem, the bigger problem. I've given you an easier problem. Now I just want to give you a structure on how to turn this into a math circle for people. Okay, you have to start with the pigeonhole principle. And kids really like this one. You tell them, hey, you've got 10 pigeons, 9 pigeonholes. You're definitely going to have 2 pigeons sharing a pigeonhole. And usually kids go, duh. So easy. I don't know why you're talking about it. Okay, and then you go into this. And then the best thing to do with this math circle is to hit some pigeonhole problems at this point. Like your basic, you've got 10 white socks, 10 black socks. How do you start out with some easy ones? How many socks you need to pull out, to guarantee a black sock. And then there's some harder pigeonhole problems too, and I put them in my presentation for you. Not this copy is a simplified version, but the bigger one on the web has more pigeonhole problems. Okay, some gotchas with this stuff. So you do the pigeonhole, and then you do the people problem. The people problem, the hardest thing about the people problem is just explaining it. You've got 6 people at a party. Either 3 know each other or 3 don't. You have to spend some time on that because that confuses people. It takes them a long time. And I've done this math circle at work with people, and even people who are really good programmers or good systems people, it takes them a long time to understand, what are you talking about, people at a party? I don't want to think about that. What do you mean? So you really have to say, I promise you, it's gonna lead to a great aha moment for you. I promise you. So you got to sell them on that problem because it kind of sounds weird. Sometimes I use handshakes because it's easier. A gotcha I've had several times with children with this, high school age children, is that I even had somebody tell me, he goes, this is totally a problem for computers. This is not a problem for humans. I can tell right away. This is a problem for computers. You give a computer this, they'll figure it out. So I was able to introduce, if you get that one, what you can say is, well, yeah, it is a problem for computers. That's great that you saw that. But we have to write the algorithm. And then you can go into a whole thing about algorithms because a lot of times the high school kids, they haven't been introduced to writing instructions out for the problem. So you can go into algorithms. You definitely have to talk about, if the kids haven't been exposed to commutations, and combinations and permutations, you have to go over that. So that's really fun, and that's a whole couple of times. Some comments about math circles in general. I really think that people are starving for math. People are starving for it. They want it so bad, but they want to know that you're not going to make them feel stupid. And even in a grocery store, with the clerk, at a health food store, I started talking about, well, what do you do? I'm a programmer. I like math. Oh, really? I like, what is that? And you can start, as long as you say, I'm not going to make you feel stupid, it's going to be okay, then they'll be willing to sit down and go over some problems, and then you can start a math circle, and then, they've got kids, and then it just goes from there. So I really think people are starving for it, but we as math people have to reassure them that it's okay. It's okay. So just like words like all are welcome, all levels, making it safe for them. And also another thing about math circles in general that I found is that we have to be ready to talk about the soft skills. And what do I mean by that? I've had kids in a circle, and then one kid is kind of slow, and then the other kids, every time that kid opens up their mouth and starts talking, the other kids are like, oh, she's talking again, she's so stupid. And I just stop that. We have to call these kids out on this early. But how do you do that, right? We haven't been, like somebody said earlier, we haven't been trained in psychology. So maybe if you're really uncomfortable talking to kids about these topics, collaborate with somebody who does do that stuff. I have 2 people that I work with the math circles, that are more comfortable talking about that stuff. And they've taught me so much. I mean, they're totally willing to call kids out on behavior, and in a positive way. So I've done all sorts of, if you want to talk about that later, come and find me, because there's so many great people that work with children who know how to deal with them, and if we team up with them, they can help us on that side. Okay, so what I haven't done is I haven't done a math circle on the bigger Ramsey problem, but one thing I did want to just talk to you about was that this people problem does tie back to that Ramsey problem, and Ramsey, they have things that are called Ramsey numbers. And so the people problem is a Ramsey 3-3, and this is like if you have a graph of 6 nodes, you have either a click or an anti-click of 3. And then there's Ramsey 4-4. There's all sorts of Ramsey. This 5-5, 6-6. There's all these numbers. I mean, Ramsey theorem, Ramsey stuff is really intense topic. There's a lot of, wait till I finish and then I'll, what?
Just wondering what.
Yeah, to be honest with you, I'm not really sure completely because it's really tough. And if you go look up Ramsey numbers, I think what this means is that if there are 6 nodes in the graph, there are 3, there's a click of 3 and an anti-click of 3. But then, what?
Are these Ramsey? They're called Ramsey numbers?
They're called Ramsey numbers.
Maybe they're like the small.
Yes. Yes. And this is the size of the graph. Okay, so Erdős, who's a famous mathematician, said that if aliens were going to come down to Earth and they said, you know what, we're going to totally kill all you guys if you don't give us Ramsey 5-5 and Ramsey 5-5. And he goes, if they say that, then we should get all the computers and all the mathematicians in one place, and we should try to find the number for 5-5, the Ramsey number for 5-5. But if the aliens came down and they said, we're going to kill you if you don't give us Ramsey 6-6, he said, you know what? We should just get the military and try to kill the aliens because it's not going to happen. If you're interested in the bigger Ramsey stuff, there is an interesting web project that's called Ramsey at Home, and it's a distributed computing system. And it's a good one. It's an open source project, so kids can get involved if they have the aptitude and the time. And it would explain more about these numbers than I can. Okay, so just in conclusion, what I've told you Ramsey theorem, the party problem, and I've given you the structure for a circle. And the only thing I wanted to end on was just a piece of advice to tell people about if you're starting graduate school, you should go ahead and keep reading. Just keep reading. Don't stop. And chapter 0.